We've seen categories whose objects are categories and arrows are functors. In this lecture, I'm going to show you categories whose objects are functors and arrows are natural transformations. In order to construct these categories, we need to understand the composition of natural transformations. So suppose we have two categories, C and D. And functors, three functors, say from C to D, all from C to D, let's say F, G and H. And natural transformations, say from F to G we have a natural transformation eta, and from G to H we have a natural transformation mu. Then we can form a natural transformation from F to H as the composition of mu and eta. We'll call it mu circle eta, and it's defined by, we need to say what it is for every object of C. So mu circle eta of every object A of C is mu of the object A circle eta of the object A. Recall that mu of A is going from F of A to G of A, and eta sub A is going from F of A to G sub A, G of A, and from G of A to H of A we have eta mu subscript A. And so it makes eminent sense to compose them and get mu subscript A circle eta subscript A. And we need to check that this is a natural transformation. So how do we check that? So claim is that mu circle eta is a natural transformation. Natural we'll use the fact that mu is a natural transformation and eta is a natural transformation. So given F, an arrow in the category C from A to B, we have F of A to G of A, we have eta A, and from G of A to H of A we have mu A. And similarly from F of A to F of B to G of B we have eta B, and from G of B to H of B we have mu B. And vertically we have the arrows F of F, G of F, and H of F. Now the fact that eta and mu are natural transformations means that this square here commutes and this square here commutes, and we can put them together to show that this big rectangle here commutes. So now what we need to show is that mu B circle eta B circle, let's just look at mu circle eta B circle F. So by definition mu circle eta B is mu B circle eta B circle FF. But eta B circle FF is equal to GF circle eta A. You can go this way or you can go this way in the square on the left. So this is mu B circle GF circle eta A. And now what you can do is you can use the fact that the square on the right commutes. So mu B circle GF is HF circle mu A. So this is HF circle mu A circle eta A. But that is the same as HF circle mu circle eta of A. And this establishes that mu circle eta is in fact a natural transformation. We are now ready to define a functor category. So let C and D be categories, and let fun CD be the category whose objects are functors f from C to D, and in fun CD the arrows between two functors, and given functors from C to D, the arrows in fun CD from F to G consists of all natural transformations from F to G. Okay, so let's so this you may think as building up several layers of abstraction, but what is it good for? Such categories are used a lot nowadays in algebra. Let me give you a famous example, which is the category of species. So this was developed by the mathematician Andre Joyal in 1980, and he used it to solve combinatorial problems. I'll say more about that later, but let's construct the example of species. The category of species is a functor category. So firstly, I need to define some categories. So FB is the category whose objects are finite sets, and arrows are bijections. So you don't allow any function from one finite set to another. You only allow bijections from one finite set to another. So you have no arrows between finite sets which have different cardinality. Of course, you still have an identity arrow from every finite set to itself, which is a bijection. So this is a category. And the other category I'll take is F set. This is the category of finite sets with functions are just all functions. Arbitrary functions are arrows in this category. Then definition is the category of species is the category of the functor category of functors from FB to F set. Okay, so this succinct definition keeps track of a lot of information. So let me translate this into plainer English. So in other words, an object in this category, which is called a species, is a rule F, so it's going to be a functor. What does it do? Firstly, to each finite set, it must associate another finite set. To each finite set, U associates a finite set which we'll call F of U. Okay, that's at the level of objects. And the other thing is, to each bijection, let's say sigma U to V of finite sets associates a bijection f sigma from fu to fv. See, a priori when we say f is a functor, then f would only associate a function from fu to fv. But since sigma is an isomorphism, f sigma will also be an isomorphism. The inverse of f sigma will be f of the inverse of sigma. And so f sigma will actually be a bijection. And what we should think of this f as putting a way of putting a certain structure on U. So the set f of U will be all the different ways of putting a certain structure on U, and this f sigma will be called transport of structure. So I'll give you examples where it will be clearer what this means. So this will be fu will be the set of f structures on U, and f sigma is called transport of structure. We are not done yet with unwinding the definition. These sets and these transport functions must satisfy certain axioms. So the axioms are axioms for a functor, namely that f of the identity of U is the identity function of fu for every finite set U. And the second axiom is that given bijections f of tau circle sigma needs to be equal to f of tau circle f of sigma. Let me give you an example of this, of a species. So this is a historically interesting example. For each finite set U, let fu denote the set of all trees. So this is from graph theory. A tree is a graph which has no cycles. It's a connected graph with no cycles. So a set of all trees with vertices labeled by U. So this is the structure we are talking about is a tree structure. So f of U is the set of all tree structures on the set U. So if we take U equals, so an example inside this example is that f of 1, 2, 3. So now we have three points, 1, 2, 3, and we want to find all possible ways of constructing a tree with these 3 points as a vertex. So there are actually, it's not difficult to see that there are only 3 such trees. One is where there's no edge between 2 and 3. Another is where there's no edge between 3 and 1. And another one is where there's no edge between 1 and 2. So this is the image of the set 1, 2, 3 on the species for the species of labeled trees. And now suppose we have sigma. Let's take sigma to be a function from bijection from 1, 2, 3 to A, B, C, another set where sigma of 1 is equal to A, sigma of 2 is equal to B, sigma of 3 is equal to C. then each of these tree structures on the set 1, 2 with trees with labels 1, 2, 3 will give rise to a tree with labels A, B, C, where you will be replacing the labels of the original tree with the transformed labels. So we'll have that f of 1, 2, 3 is equal to A, B, C. So this is f on the level of morphisms. And similarly, you can do f of 1, 2, 3 would be the tree A, B, C, and f of so the structure on the set 1, 2, 3, the tree structure on the set 1, 2, 3 is transported to a tree structure on the set A, B, C using the bijection sigma. Now this might seem all very simple. The definition is just a line once you understand what functor category is, and however it turns out to be very useful, and there's a nice reference for applications of the theory of species is the book by 3 authors, Bergeron, Labelle, and Laroux, and it's called Combinatorial Species and Tree-like Structures. To give you an example of the power of this theory, let me mention that André Joyal, in his original paper where he introduced species, he used this theory to give a very, very beautiful bijective proof of a theorem of Cayley. So here's the theorem of Cayley. The number of trees on n labeled vertices is n to the power n minus 2. And Joyal used the theory of species to come up with a very, in a very natural way, with a bijective proof of this theorem. So you can look at this book, or you can also look at the famous book by Aigner called Proofs from the Book, where Joyal's bijection is given but without any mention of species.